I think we should get started now. Okay, good afternoon, everyone. Very warm welcome to this session of Data Dialogues. I am very excited to welcome Professor Ayantika Chatterjee from IIT Kharagpur to this session of Data Dialogues. The title of her talk is Homomorphic Encryption, the Holy Grail in Real Life. I'm really looking forward to the talk. But before that, I would like to introduce Professor Ayantika. Professor Antika has received her PhD in Computer Science and Engineering and MS degree in Information Technology from IIT Kharagpur. And after PhD, she joined Data Storage Institute, Agency of Science, Technology and Research, also known as A-STAR in Singapore, as a scientist and worked in the domain of encrypted database design. She was also associated with Indian Statistical Institute, Kolkata, as a postdoctoral fellow. And at present, she is working as an assistant professor at Advanced Technology Development Center, ATDC, IIT Kharagpur. Her research interests include embedded security and secure cloud computation. And I've already mentioned the title of today's talk is Homomorphic Encryption, the Holy Grail in Real Life. And I'm really looking forward to it. At IUDX, we deal with data a lot, exchanging data a lot, and privacy preserving computations and privacy preserving machine learning is really of interest to us. I had a chance to attend this one talk from her recently in IIIT summer school, and I'm really looking forward to it. So with this, I think I welcome Professor Ayantika once again. And over to you, Ayantika.
Thank you very much. Hope I'm audible, and
Yes,
I'm just yeah. I'm just stopping the video for the saving the mind video. Okay, so so welcome to this talk on homomorphic encryption. Here we are going to talk about. First of all, we will start with the concept of homomorphic encryption and why we consider this as the holy grail in the domain of cryptography in case of giving confidentiality to data. And then we will be talking about adapting or the limitations, to be specific, of adapting this encryption scheme when we are going for some real life computing. Okay. So before going to the actual talk, a few facts and figures. So there are two takeaways just from this slide, that recently the reported breaches, I mean the day by day, the reported breaches on data, those are gradually increasing. From this is just a few figures related to few months of this 2022, and also the on top of that, the loss we have to pay, maybe to compensate the breaches, that compensate the leakages, or in with respect to from the demand coming from with respect to some attacks. So the amount which we have to pay, that is getting huge and in order of billions. So in that context, and also on top of that, for generating our future insight, data is our new treasure. So data security is needless to say why it is of so much concern. Now, before going to the what may be the solutions for the data security, we may talk about few recent hacks or leakages, reported leakages. So from this table, if you just go by the organization names in this table mentioned, so there are different ITBDs names associated: Yahoo, eBay, Uber, and there are also many more: Microsoft, Dropbox, LinkedIn, and many more. And if we go one by one, there are different leakages reported from their own server. That may be related to some user accounts, related to some passwords, or user details. Those can be considered as a confidential. Now, here I have not listed many more data leakages from different medical organizations. And those type of data is also of serious concern because not in India, we do not think much of it to be specific, but brought this medical data. This is considered to be very confidential and critical data. And when any organization are facing these kind of leakages, hefty amount, as I was telling from the first slide, that it is order of millions they have to pay. So for this reason, we are interested enough to how, in spite of the fact we need to do some processing on data, we have to share, we have to outsource data, how to keep them secure. And the problem comes, very prominent when we talk about cloud or cloud computing. When we outsource our data, we need cloud, we pay to cloud, not for storage only, but for storage as well as computing. So when we are uploading the data, we are giving access to our data to cloud. Of course, our data is getting exposed to some specific public platform. And from the previous all these examples, what we have seen, that in spite of the fact the clouds they are promising, they are having some access control, they are having some their inbuilt security solutions, still they are not enough. So what is the solution? The first solution that may come up in our mind, that we can store the data in some secure form, and to be specific, providing the mathematical security guarantee by some encryption solution, where we can store data in the cloud in some form of, in some encrypted form. Now that brings another problem, that when we are putting data in some encrypted form, that is, if and we are going by our traditional encryption schemes, these encryption schemes, they can generate some random cipher map from our whatever data, plain text data we are using. So this random number we may store, that is good enough to confirm the storage security, but not the processing security, because we cannot process on that data. And for this reason, we need some encrypted form of data where we can not only store but also process on that data. So to start with, what is the solution for that? The first solution that may come up in our mind, or maybe if we just go by our history of our proposed crypto systems, if we start with RSA, that was, sorry, yeah, RSA was proposed, that was from 1977. So we have some tool. So we have some tool, but if we just follow the RSA crypto system, that is one traditional crypto scheme, and we see the ciphertext that is getting generated, or the encrypted form by in which we can store the data. This looks like this. Okay, when X is our plain text that we are trying to upload, and that X we can upload in this type of X to the power E modem, this type of ciphertext form. Okay, and if we have these type of two ciphertext, you can see here this one and this one, and if we are multiplying this two, basically we are doing this kind of operations, and by the simple arrangement we can get the encryption of multiplication of two plain text. That means when we are uploading two ciphertext, maybe C1 and C2 under this RSA crypto system, and if we multiply them, we can get that is equivalent to doing the multiplication of the related plain text in plain text domain and then encrypting them. So basically what we are supporting some amount of computation, but for that computation we are not taking the data back in the plain text domain, we are doing the computation keeping data as it is in that encrypted form. Similarly, we have some solution for addition. Okay, that is, you can check the year here, that is 1999. Then this this solution, this crypto system proposed back in 99, where if we now check the here the ciphertext structure, basically yeah, the ciphertext structure, this and this, and if we do some typical multiplication computation, just simple arithmetic, then we can get some this type of structure of the final ciphertext. That means if we upload two ciphertexts in the cloud under this additive encryption form, and then if we perform some multiplication operation in cloud that is equivalent to doing the addition of these two plain text and encrypting them. That means if I have uploaded few data under this encryption scheme and I want to add them, no need to take them back to the client side and then to encrypt, but just I can do some equivalent. Not telling that exact computation what I can do in plain text. I am doing the same computation, but equivalent computation in cloud side will give me the addition result. So that way, well, the if we need some specific computation to be done on the data in secure form, the solution we had back from 90s. But what we are again, why we are again revisiting this homomorphic term in this recent years, this is because these are two different crypto systems I am talking about. Like under one crypto system, you cannot have the flavor of both addition and multiplication to be done in encrypted domain, to be done on the secure form of data. And that took almost uh, around till 2009, sorry, when the concept of, or to be specific, the first plausible construction of fully homomorphic encryption was shown, which supports both addition and multiplication in encrypted domain. No need to take your data back to the client side. If you are encrypt your data under this types of schemes, encryption schemes, then you can actually process addition and multiplication both in the secure form, using the computation power of the cloud. So that's why, and I will come back to the general concept of homomorphism later. But first to tell about the advantage of FHE is that you are using now the resources what you have hired from cloud, and you are doing the processing there, and you are also confirming the data confidentiality. Your data is not getting exposed. Now, why this FHE, fully homomorphic encryption, that we term as the holy grail of cryptography? Because theoretically, with this concept by its first plausible construction, it was considered that it can actually support arbitrary computation, because when we can do addition and multiplication together under one single encryption scheme, basically the idea is we can extend that to some universal gate concept, and from there we can there is a, we can directly show that theoretically we can compute any arbitrary computation in encrypted domain. That was the theoretical idea, and that from that theoretical idea, I mean, uh, from there we will start our discussion, and in this talk we will see how far this assumption is really true. In spite of the fact theoretically this scheme can support any arbitrary computations, but when we are talking about this sort of practical requirements, like we are nowadays cloud is giving our different us different services like database as a service or price based preserving machine learning. Just now there is a mention about that. So when we are really trying to adopt this type of encryption schemes in these applications, how far it is true that this FHE scheme, the theoretical claim, how far it is true that it can truly support all types of privacy preserving computations. Okay. So in that way, when we are talking about homomorphism, basically homomorphism theoretically, this is a mapping between two groups, where it is same as doing some computation and then applying some function is equivalent to applying that specific function on two or more data and then doing some equivalent function. Like if you just replace in this slide this function if with the concept of encryption, it is same as when you are doing G1 into G2 and you are applying encryption. It is same as you are applying encryption on G1 and encryption, you are computing encryption of G1 and you are computing encryption of G2 that you have already uploaded in cloud, and you are doing some equivalent computation in cloud. No need to do that in the plain text domain separately. Now with this concept, let's check what we need to do in FHE domain, or to be specific, how FHE, the homomorphic encryption, a bit different from the traditional encryption. What extra we need to compute, because that will give us the idea what are the challenges we are actually facing and what is the reason of the challenges we are actually facing when we are adapting or trying to adapt this homomorphic encryption in our real world computing, real world problems. Okay, so let's start with this very simple concept, simple maths. So you can see here, these are the two cipher text. Okay, this C1 and C2, and they are encrypted under this encryption concept, encryption algorithm. So this C, any cipher, the cipher text is getting generated by P into Q plus 2R plus M. That means we are encrypting a particular bit. Let's consider whatever data we are dealing for the timing, that is in the bit level representation we are considering. We can always extend that to some integer level or some higher level. But here we have taken the simplest example, that is a bit that is getting encrypted with this secret key, that is P, and also P into Q. Q is a large number, and 2 plus 2 are, these are the requirements to provide the randomization in the encryption scheme. So I'm not just going to the detail of the encryption scheme, just we are interested here to analyze the structure of this generated ciphertext. Now, what is our purpose to do? Why we are applying this homomorphic encryption or using this homomorphic encryption? So that we can do some computation in encrypted domain. And when we are talking about fully homomorphic, we are interested in both addition as well as multiplication. So if we now see, if we are just adding two ciphertexts C1 plus C2 and C1 into C2, so just adjusting these terms, we will get this type of expression in the right hand side. You can see C1 plus C2, some term associated with multiple of P, and M1 plus M2, that is addition of the plain text bits, along with some randomized term, that is 2R1 plus R2. Now, according to the decryption step, if you see at the left side, so when we are doing the decryption, we are doing some mod P operation and then mod 2 operation. Similarly, if we apply this mod P operation first on the C1 plus C2, we are getting some addition of plain text along with some randomization R1, R2 related term. Now, for the time being, we are specifying this term as error term. Gradually, maybe in the next slide, it will be clear why we are pointing that as error term. We will come to that. Before that, the similar things are happening when we are doing this C1 into C2 computation. This one, okay, C1 into C2 computation. Similarly, we are getting some multiples of P. We are getting M1 into M2 and then some error term. In the next step, when we are doing mod P operation, we are getting back M1 into M2 plus again some error term. Now, if we can put this error term within a particular range, okay, within a certain threshold or within a negligible range. And if we do this mod 2 operation on top of this C1 plus C2 mod 2 expression, basically this error term will vanish and we will get back our M1 into M2. So that means whatever, now this shows that whatever operation we are doing in plain text domain, like M1 plus M2 or M1 into M2, the same thing we are getting when we are doing in the encrypted domain. We are doing the C1 into C2 or C1 plus C into C2 operation. Okay. So this is the basic requirement of our homomorphic encryption scheme, that whatever we are doing in the plain text, similar things we can replicate in our ciphertext domain. But there is one problem or one point I've mentioned, that is we have to keep this C1 plus into C2 in this expression, this error term within a certain threshold. Now, what is the purpose of this certain threshold, or what may be the value of this certain threshold? Now, if this is greater than P, sorry, if this is if this is greater than a certain threshold, like if it is greater than P, then with this simple deduction, we can see if this value is going beyond a certain threshold, that may lead to some bit inversion. Okay, that may keep one extra term in the result computation of M1 plus M2 or M1 into M2, the similar thing we can see, and that may lead to a bit inversion. What we mean by bit inversion? That means if I was expecting, since we were talking about bit level operations, addition or multiplication, if we just add one extra one here, so that may lead to one may get flip to 0, or 0 may get flipped to 1. Now, if this bit or inversion is occurring, that means we are not able to keep that error term within a certain threshold. That means that indirectly showing that the homomorphy of the scheme is not retaining. That means we are not getting the equivalent result of our plaintext operations. So that's why it is important to keep that error term. Sometimes we term that as noise in homomorphic computation to, I mean, within a particular threshold. And here comes the problem of homomorphic encryption scheme. This is the only requirement, this is the one sole requirement that makes a scheme homomorphic. That is a boon of the homomorphic encryption scheme. And that is also the curse of this homomorphic scheme. The reason here is, if we just see the right hand side problem, that we are telling that we will keep that noise level within a certain limit. Okay. Now, when we are doing some ciphertext computations in encrypted domain, let's say C1 into C2, C2 into C3, gradually, if you now just observe this expression, if we are doing some more computation at a certain point of time, it may happen that this error term is growing bigger, okay, than the threshold. And that's why we have to keep some mechanism that will hello.
Yeah, we are able to hear you, President.
Okay, fine. Okay, yes. So we have to keep this error term within a certain limit. Now the question is how we can keep them. Basically, to do that, we apply these kind of techniques to handle the noise module, and we term them either, here we have termed them as recryption, re-encryption, sometimes to make the scheme sustainable, bootstrapping operation. So these are different terms you can see in homomorphic encryption literature. all of them, for all of them, the main purpose is to keep this noise within a certain threshold. On the other way, other technique what we use, if you can see the right hand side this diagram, when we are doing this ciphertext bit-based computations, we are generating some new ciphertext, right? Here, when we are doing this ciphertext bits, on top of them, we are these are the encrypted ciphertext bits, and on top of them, we are doing some computation, addition, multiplication, combination of both of them. Because now in by fully homomorphic encryption scheme, we can generate different computations, right? And in turn, we can realize different logics. But while doing so, some intermediate computation output, maybe that is some C we are getting. We have to ensure the noise level what we are getting in this ciphertext, that should be within a certain threshold. So to guarantee that, one way is that always take the ciphertext, do some operation on that, and generate one equivalent ciphertext. Equivalent ciphertext means the C and C dash, if decrypted, will map to the same plaintext. So while getting that equivalent ciphertext, we have to do some processing so that the C dash, the equivalent ciphertext, should have some lower noise level. That way, we are ensuring after every computation, or sometimes we do that after certain levels of computations, that we ensure that now I will generate a new ciphertext, now equivalent ciphertext. And this new ciphertext will have the error limit, or the error within that ciphertext, error term within the ciphertext, that is always greater than certain threshold. And these operations can be done, or theoretically, if we conceptually we think that how we can get this type of ciphertext with much lesser noise level. For that, we have to decrypt one easy way, theoretical way, that I can decrypt the ciphertext and then I am encrypting back. When I am encrypting back, I'm generating a fresh ciphertext. Of course, that should have certain lesser noise level. But here doing that in cloud, the practical problem is that for decryption, you need the secret key. And by assumption, the cloud or the processing server where you are keeping your secret data, encrypted data, you should not keep the secret key there. Because otherwise, if the cloud is having both, that is the secret key, the cloud can decrypt that data and get back the plain text again. So there is no security at all. So now we have to decrypt the ciphertext C in such a way the secret key should not be given to the cloud, but the decryption will still happen. For that, what we are doing, we are not giving directly the secret key, but we are giving some encrypted form of secret key that is operating on this encrypted, this ciphertext C, and we are getting back one C dash, another ciphertext, that is again the encryption of same plain text, but with some lower noise level. So that's why these term or these operations we term as re-encryption. That means I'm decrypting and re-encrypting. And from there, these term comes recryption, re-encryption, etc., etc., and also bootstrapping, because that makes this homomorphic scheme self-sustainable. Because if you are doing this after each and every operation, you are always sure that okay, whatever ciphertext is getting generated, the noise level is lower than the threshold, so still the scheme is retaining its homomorphic property. Okay, so as I was telling, this is the main crust of homomorphic encryption. What makes this is the main operation, this bootstrapping, recryption, whatever we may tell this. Let's consider this term that for the next onward discussions, bootstrapping. These operations is basically the main reason why a scheme, encryption scheme, is retaining its homomorphic property, why it is different from the traditional encryption scheme, why it supports encrypted domain computation, and also the second, and we will go to the next slide that will define the challenges and recent research focus in homomorphic encryption domain. Okay, so here we see the recent research directions of homomorphic encryption basically divided into two parts. Okay, the first part in the left side you can see that is the homomorphic scheme development. That means the conceptually whatever I was telling so far, like doing this decryption, encrypting ciphertext, support giving some information of ciphertext to the secret key, and then doing the next level processing so that we can generate a ciphertext with some lower noise level, etc. So these homomorphic scheme development is one major research direction where the objective or the challenges of designing this sort of homomorphic encryption schemes are twofold. Okay. So this left-hand table, I mean, there's the flow. If you see, so as it started with 2009, then 2009 2011, it was the major initial step of FHE research where first plausible construction was proposed. After that, the second orange line, those FHA schemes, those are developed based on AGCT problem. That is, the underlying mathematical notion is based on approximated GCD problem. Okay, but the main focus there was to reduce the public key size, okay, and also the ciphertext size. So as I was mentioning, this for the scheme development, there are two main challenges. The first is the how we can reduce, because here the ciphertext blow up size is very much huge. Maybe for there are different schemes we work today where 1 bit ciphertext is getting mapped to at least to some more than 250 bits. So and even more than that. So that is the in blow up in the ciphertext size, blow up in the key size, and also the blow up in the performance time, because when you are doing this bootstrapping steps, there are huge mathematical computations involved. There are huge large multiplier computations involved, and for this reason the overall this bootstrapping makes this homomorphic encryption, I mean memory hungry as well as computation time hungry. Next comes in this green line, these research directions, that is starting from 2011 onwards, that is basically to develop FEG schemes based on learning with error problems. Okay. And this, I mean, uh, genre of research, they mostly focus on how to make these reduce the noise growth, how to control the noise growth, how to improve the, I mean, reduce the timing requirement for bootstrapping, and also some of the contributions side by side. They take care of how to reduce the key size and how to handle this huge ciphertext blow up. To keeping mind about the and keeping in mind about the memory constraints, memory requirements. Okay. And the fourth is based on NTRU. So they are very specific types. So I'm just focusing on this LWE schemes and also some AGCD based schemes, and how we are translating this FHA concept based on this scheme to this real world computing or practical computations, real world algorithm realization, etc. Now, whatever, okay, after that, 2015 onwards, some compilers also have been developed, and one major direction of FHE libraries have been proposed in context of this TFHE or FEW. So, this what is the difference between this TFHE and the previously mentioned all these schemes coming from previously LWE based schemes or AGCD based schemes? Prior schemes they have handled these operations based on integer form. Okay, and also they are very operation specific. That means the operations supported by these schemes, those are either multiplication or addition. In our coming discussion, we will see just restricting with that these two operations, in spite of the fact theoretically it can be argued that this is the basis of any arbitrary computation. But why are the challenges? But in TFHE or this few these type of directions of library, they started supporting binary bootstrapping. That means the example we have seen before, whenever you are doing bitwise operations, maybe bitwise addition, bitwise multiplication, after each bitwise operation, you are applying this bootstrapping technique. That means noise handling technique. That means now you are retaining your homomorphy in the noise bit level operations, and if you are extending that to integer level or higher or fixed point level, of course that bitwise homomorphy is getting retained. Now it is shown that in future this TFHE or this few types of schemes, they are they are they are a better choice. They are basically better choice to be specific TFHE, because TFHE is basically the advancement of few. So this is a better choice for complex application development rather than the previous schemes where we can develop operations, but as a for an end-to-end algorithm realization, they have some limitations. Okay, so we will come up with that discussion after a certain after a few slides. But the main challenge here with this FHE research or direction of research is this: whatever types of, maybe it is AGCT based, maybe it is LWE based, or maybe it is integer level handling, maybe it is bitwise level handling, whatever support we are getting from these FHE libraries, they are supporting either bit level or integer level only additions and multiplications. Okay, and that defines the next direction of research, that in spite of the fact we can argue that these addition and multiplications are good enough for universal get realization, but what about an end-to-end encrypted domain algorithm realization? And that is our main objective, because when we are hiding cloud or any public server like cloud, when we are taking their service in terms of database, in terms of machine learning, we are not expecting that okay, I will just do one addition or one multiplication. There is a series of operations, series of requirements that may be satisfied, that need to be satisfied to realize one end-to-end algorithm in encrypted domain. Okay, so we will talk a bit about those, that what are the requirements and where we are limited enough in homomorphic domain. Okay, so this is the requirement. If we just start thinking about what we need to do to translate one algorithm to encrypted domain. From our basic writing C programming, when we do what we have some algorithm, we define the algorithm operations, then the algorithm steps we map to some operators. Like if we just take the basic example of C operators, so we have that our arithmetic, relational, logic, bitwise, etc., these operators, we just map our instructions or algorithmic steps to these operators. Along with that, what we need? We need to handle those operations, maybe sometimes in loop, sometimes a single operation. So we have the next requirement is the loop handling, or the third one, some conditional if else, those requirements, conditional statement handling. So when we have to translate one algorithm to encrypted domain, we also need to think that okay, not only these operations are sufficient, we have to handle this if else condition checking, we have to handle this loop handling. Everything should be realized in encrypted domain, encrypted. Now, and if you go deeper about these operators, there, I mean, for each and every operator, they are not straightforward. Even what we do to be specific about the multiplication and division operators, we always try to design our encrypted domain algorithms in such a way so that we can bypass the division requirement, because division is still too much. It's costly. It requires huge number of computations. One single division. So that I'm not due to the timing constraint, I'm not going to the details of FD operators. Just to give you an idea about the feasibility. One thing is here, we will talk about the feasibility, and the second thing is the performance. First, I have to make something work, and then we will talk about the performance. Okay. So there's one example we can take, one simple example, like about I was talking about the loop handling, right? So here, at least the division example is given. So here you can check this part. These are the other, this shift and add, etc. These are the problems. It is mentioned about multiplication, termination conditions, etc. I'm just taking the example of division. When you are going to divide something, numerator and denominator, basically in traditional concept is we will just do repeated subtraction, right? And this repeated subtraction operation will stop when you have this n greater than equal to d. This condition is getting satisfied, right? Between your numerator and denominator. But in encrypted domain, your problem is the numerator and denominator both are encrypted. Now, when you are going to do this type of computation, this you are going to check. So, with some you have, let's say you have developed one comparator operator in encrypted domain, and when you are doing this comparison, you are getting some encrypted result. Okay, and this encrypted result is basically to be realized by your underlying processor, the platform you are working on. And that platform, when you write, if you, I hope you have, so when you are writing any C code, C++, any code, when you are handling this type of while loop, this while output is basically 1 or 0, either some 0 or non-zero value. So whenever this underlying processor in this encrypted case is getting some non-zero output, it will consider that it will never consider that as the ending of the loop, and that way it will go into it will start running into an infinite loop. So that way the simple termination, loop termination, that may be for while loop, that may be for while loop, for any case, that will not directly work when we are going for this encrypted domain. That means this loop handling itself, whenever you have in your algorithm some loop handling, you have to revisit that, so that you have to make some assumptions based on your application, or there are different techniques we apply. There are different types of solutions, but somehow that the core whole point is that how you will be handling this loop, that is also not so straightforward, because after all your underlying processor is unencrypted. So that requires a revisit of each and every traditional unencrypted domain algorithm when we are translating them to encrypted domain. Okay, this just the loop handling. I have giving just one single example. In this paper, actually, we have mentioned the challenges for each and every operator. Okay. Similarly, if we go one step higher, if we are now thinking about cloud services, because there is our purpose to apply homomorphic encryption. Our purpose is that when I am taking any service from cloud, I will take the service, but I will not expose my data. So that means when I am going for this, taking this database as a service, and I am trying to upload my data, I will expect that this type of select, update, wherever query processing is possible, that will happen on my data, but my data will remain encrypted. To be specific, the database I'm storing in the cloud, that will be like this form. You can see I will have all these columns, but all the values will remain encrypted. That is my ideal expectation, because that is fully homomorphic encryption is claiming as a holy grail. It can support any arbitrary computation. So these query processings are also one part of arbitrary computation. So that should be realized. So that is the theoretical claim. But in practice, we will see for each and every query execution, there are different types of problems. Okay. For example, in select query operation, we need to have, whenever we will apply these queries, the output will be some non-zero values or zero values. Like for if there is a match for a particular condition, or there is not match, then the row will get selected or the row will not get selected. But in case of encrypted domain, the problem is for whatever comparison you are doing for the conditional select queries, for each and every condition checking, there will be an output. Now that output may be either encrypted zero or some encrypted non-zero value. In case of encrypted zero situation, in plain text domain, the easy thing was that rows are not coming out as your output. So for a particular query, when you are applying some query, if your database size is of n rows, you are getting some m rows as the resultant output, where m is much lesser than the whole row numbers. But here the challenge is that whatever n rows, you are getting some entry for each of the rows, whether there is a match or there is a no match. The reason is that if we can isolate that, there is some theoretical proof. If we can isolate that, if we can separately select a few rows based on some query execution, then that will lead to some underlying attack. Okay. So we have to revisit this select query execution also to check how we can make this efficient without violating any underlying security requirements like CPA, CCA. Those are the typical basic security requirements when we adapt any encryption scheme. Okay. Similar problem. Also, these are the experimental results shows that along with these feasibility issues, the operators that we can do, that we can actually implement, they are very performance hungry. So our next challenge is how we can make them performance efficient, or what are the techniques we can adopt. So that is the indirect, another direction of research, or we may say that is a related direction of research in FAG domain. But before going to that, we will talk about encrypted machine learning. Okay, because privacy preserving machine learning, that is our nowadays requirement. So when we are talking about machine learning as a service, how we can take the service from the cloud, again keeping our data encrypted. So here we have taken one example of k-NIN computation, and where we can see we have first, again from the algorithmic steps, we are observing that what operations we need actually to map this k-NIN to some encrypted k-NIN. And the left hand side, from the flow, you can see what are the operation requirements. we have no time to go for the details of all the operations and to take the challenges. Just one example I will take here. In one part, we need for KNN we need to sort the distance. Okay, because we based on the k value. First, we will in KNN algorithm, what we do, we take some distance from the test input, then we sort the distances and we take the k nearest values. Okay, so sorting one essential component, essential operation we need to do to in encrypted domain, of course, right? To realize KNN as an encrypted KNN. So where is the challenge, or where is the difference to implement sorting in encrypted domain? So first of all, we all know that general concept of sorting, what we have in our traditional unencrypted domain. We know that if usually we go for some choose from some sorting technique, we bubble sort maybe will be our last choice, right? So we will choose some quick sort type of solutions, because those we know from our traditional knowledge that that will give us order of n log n complexity. But the problem in encrypted domain that shows our analysis shows that if we go for partition based sorting in encrypted domain, first of all, partition based sorting in whichever way you try, that is infeasible in encrypted domain. The reason is that, or if we give a proof in some other way around, if that encryption based sort is actually possible, that may lead to some chosen plain text attack under the, against this underlying FHE scheme. And this FHE scheme, there is a certain theoretical proof that is proved to be CPA secure, and that leads to the contradiction. And there is a from that direction we can actually formally prove that partition based sort is infeasible in encrypted domain. Just to understand it very superficially, okay, if we now consider that okay, partition based sort is possible, so what will happen? We will have one data, maybe some data, and we will have a pivot if we take the example of quicksort. So now both are encrypted, my pivot and the data. Now if I can do the partitioning, that means we can actually one I can, without knowing some secret key, without in the encrypted domain itself, I can get the idea that the data where should I put, whether the data is less than the pivot or the greater than the pivot. If that knowledge is known, basically from there, that can lead to some CPA security. I mean issues. Okay, so that is the finding. I mean the proof is it will take some time to explain, but the core takeaway is that these type of traditional beliefs or traditional proofs what we have in our plain text domain, the operations that we directly adapt in our next level implementation, that operation basic operations also we need to revisit when we are talking about homomorphic domain realization of any real world algorithm, any basic algorithm. When we are implementing, it is not that we can consider the previous modules, because these previous submodules like sorting here is a typical submodule in this KNN computation. That also we have to revisit, and we have to check how we can realize this sorting technique in encrypted data. So this is the one problem I may have mentioned for KNN. Similarly, if we are considering encrypted machine learning as a service, so there we have revisited this ASVM, we have revisited regression. In regression, not only you no need to go to the regression also. If you just know need to compute some exponent e to the power x, that is also a major challenge in encrypted, and that needs some workaround. Similarly, for SVM prediction, when we are thinking about anything higher order kernels, that is still not fully feasible for SVM purpose. So, like this, so basically speaking, whenever we are thinking about privacy preserving machine learning, it is not straightforward like from the whatever knowledge we have from our plain text domain. We need to explore or revisit all these existing algorithms in the encrypted domain with the encrypted data as inputs or encrypted flow as the input, and then we have to check that whether this algorithmic flow is at all possible or not in our existing process. So here is that this is the major challenge of realizing the traditional algorithms in encrypted domain. So this is this one what I have mentioned, that is about the feasibility. Okay. First of all, we need to check whether all these operations are feasible or not. And next comes the performance. How we can, in spite of the fact some operations are feasible with some given workarounds, what about the performance? So that is the next or the another present direction of research. So if you see here, just in this table, SVM prediction time, for this one test data for one single prediction, initially it took around 9 minutes. From there, this 1 minute 35 seconds, this type of prediction under the mentioned platform, we are getting after using some approximation in the underlying multiplication module. Like the multipliers, the basic adders we are using here, we are approximating them, then we are using. So that approximation there, that is giving some amount of performance boost up. But the problem here is that is also incorporating some amount of errors, some error probability due to that approximation. So it is not that these type of one performance boost of technique, like using some approximated circuit, that we can use for all the applications. Because in SVM or this type of machine learning applications, these are fault tolerant in nature. Okay, so there we can check that if we can introduce some amount of error, still we can get some acceptable accuracy. But the problem is this type of assumption of approximation or solution of this approximated computation, we cannot adapt for all types of computations. And here is one major challenge of homomorphic domain computation. That is, one thing is that the feasibility, and that if something is feasible, what about the performance? And we are applying some approximated knowledge on that performance. That is very much application specific. That is one solution you are providing for a particular maybe ML technique that may not work for your database as a service. Okay, so this applications, the solutions are also sometimes become application specific, application ever solutions. Along with that, some general solutions we take to improve this performance bottleneck. The one major thing is among them is the choice of the library. So as I have mentioned different in the literature, we have different types of library, and the way they are representing the ciphertext, the way they are handling the bootstrapping, those are different. And when we are designing one particular application based on the data, we need to know what type of application, what type of operational requirement of that application, and based on that it will be good to choose the library based on that. Because this is just one example from why I'm mentioning about that this choice of library is important. This is one this time in inference time we are trying to realize one CNN architecture, CNN prediction in encrypted domain. For that, we have considered this PyFHE one. This is one extended version of this TFHE library, and that took the direct implementation. Some part we have implemented and after that we calculated, it took around 120 hours. From there, the same implementation we have taken with NUFHE, which CUDA supported the TFHE version. Without any edit trick, we have applied. Okay, so that reduced with that CUDA support, it reduced to 80 hours. And after that, on top of that, we have added some amount of bit slicing technique, where we have a bit slice the representation of the, though we have taken integer inputs, after that we have bit sliced, and then we have packed some bit representations, so that ultimately our objective was to reduce the overall number of bootstrapping. And after doing that, we can I mean we can this packing with this reduced number of bootstrapping, numbers of bootstrapping, we the same prediction now we can do with this around 2-3 hours. Okay, so this is the importance of what type of library is choosing. And most important thing is that bit slicing technique cannot be directly adapted in that PyFHE version. Okay, so how that library is representing the data, handling the bootstrapping, and representing its ciphertext, that also matters. Another choice of library, okay, that is we will come after that. Another point, we will come back to the slide again. Another way of accelerating FHE is with FHE support, FPGA support. And that is, we know that the bootstrapping is the main performance blockage. So some research is going on where we are taking that bootstrapping isolatedly, and specifically not the whole bootstrapping step. Inside bootstrapping, we have some large multipliers. So those multipliers are taken separately in the hardware platform, and now FHE, this processings are getting realized by hardware software co-design. And with that, we are trying to improve the timing for this particular multiplier. And since these multipliers are heavily used in the bootstrapping technique, that is enhancing, that is accelerating the overall bootstrapping module, and that in turn enhancing the overall processing of this FHE framework. So this is one way of what is, way of accelerating the overall performance, application performance, by just not only restricting ourselves in the software design. In the previous technique, we are applying some architectural tweaks to our software design. But here we are talking about realizing the costly module in just separating and taking them in the hardware platform, and then making an overall hardware software co-design. So this is one example of this previous work I have mentioned. It is basically a separate contribution, and this is a general contribution coming from Intel, where they have proposed one FPGA, the library for this FPGA based acceleration. And this is the architecture where they are taking multiple types of FPGA libraries, and they are offloading some part to the FPGA, this key switching, this type of intermediate processing in FPGA to accelerate the overall FPGA scheme. Now, finally, as I was telling, this is the previous slide, when I was mentioning that choice of library is important. One choice we have shown that how it can help in performance improvement. Here we can consider the another type of choice, another type of framework design is possible, or there is there's some in literature that support. That is, we take some first limited homomorphic scheme based libraries. By limited we mean, that is, up to some level the homomorphy will be supported. And these type of libraries, they generally support limited operations also, that is addition, multiplication. Okay, this type of library, see, this BGV, BFV, CKK, they support multiplication and addition. So So when we are developing some overall algorithm realization only with these operations, some general technique is that do some computations in cloud, and for intermediate some complex operations that is not supported by this crypto system, take the complete computation back to the client side, get some decryption done, get some result from the client, and then to the offload the next level computation to the cloud again. But these types of implementations, when there is some handle to some decryption query, decryption oracle, so there are some this type of research that shows that questions about the security of the overall implementation, because that shows that with this the intermediate decryption query, and there are different timing techniques, some error based analysis, so there are different some more literatures are also present, but in gross they are telling in such cases there is some possible leakage, and that leakage may help to reduce the overall security of the scheme, and that may even leak the bit of the secret key. Okay, so it is also important for the choice of library when we are making for an overall FHE framework design. Not only we need to restrict or focus on the performance, of course, that is the first first and prime focus. First thing is the feasibility of application, and then the performance. Those are the first prime focus we are concerned. But along with that, we need to also check that whether whatever we are library we are choosing, or similar example we can take for database as a service, when we are allowing some database update operations, how far we are allowing in our overall FHE framework, so that maybe this choice of library maybe giving some extra boost up in the performance, this type of allowing this type of query executions, maybe adding some extra feature in our framework. But we have to also take care of the thing that we have to check whether they are reducing the overall security or they are leading to some extra leakage, so that in spite of the thing that we are adding such a holy grail type of security solution, still the overall framework whatever we are designing, whether it is still remaining secure. So that way when we are talking about FHE or homomorphic encryption in context to data security, I want to conclude my presentation with this note that this homomorphic computation or FHE based application design, it is not a mathematical problem only that we are just focused on improving the bootstrapping part or handling the re-encryption part well. It is a problem of handling the efficiency at the basic level operations. It is also the problem of the software implementers to check whether about the feasibility, how far any application is feasible in encrypted domain. It is also a problem that how we can improve the performance of the implementation with the software hardware co-design. So it is a matter of the hardware design. Also, overall, it is a problem related to the security expert to analyze the overall scheme, what have been implemented, to check in spite of the we have implemented all the sub modules with some security solutions. With this costly, in fact, FH is to some extent costly security solution. Still, it is. We need to analyze it in a higher level from the application level, whether still the overall application is still remaining secure or not. So, with this note, I want to conclude my presentation. Thank you. So, you can ask if you have any questions.
Thanks, Prof. Antika. This is Anshu from IUDX. Thanks for the insightful talk. You mentioned that one of the challenges here is to come up with an efficient implementation of bootstrapping. where we re-encrypt the information such that the error term doesn't blow up. You also mentioned the important point that in these servers, for example, if I'm running some application on the cloud, we don't want the secret key to be revealed to the cloud to decrypt and then re-encrypt. So can you give? Oh.
Hang on,
Meeting is being recorded.
Hi, Prasantika, you're able to hear us?
Yes. 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 Yeah.
I think you have to.
Hello.
Oh, there's a lot of echo. Okay, now it's gone. Yeah. Maybe you can stop sharing the screen because maybe it's.
Hello.
Hello. Hello. Hello.
Yes, Abhay.
Hello.
I can hear you. Yes, Prof. Antika, we can hear you now.
Can you hear me?
Yes, we can. You have, I think, 2 sessions going on. That's why there is an echo, I guess.
Hello.
Yeah, we can hear you, Antika. So maybe you can hear us, then Anshu can go ahead with the question.
Yes, Prof. So my question was regarding.
I think she can still not hear you because we can see her joining.
Maybe you just wait for.
This meeting is being recorded.
Hello. And
Hello.
we are able to hear you, but I think you have 2 sessions going on, therefore we have a lot of echo.
Oh, for me. Okay. Just a second.
Yes.
Hello. Can you hear me?
Yeah, we can hear you. We can hear you and we can see your screen also. It's okay. Yeah.
Hello.
Hello.
I have 2 sessions. For me. Hello.
Yes, we can hear you.
आपका सेशन तो मैं खुला नहीं की बोलছি
This meeting is being recorded.
Hello.
Yes.
Still the same problem, right?
Hi, Anshika, can you hear us?
Yes.
Okay. I think there's just a lot of echo, and I think it's because I can see you logged in twice, and I think that's why the echo is happening, Anshika.
Okay. Just. Can you hear me now?
Yes.
Hello.
Yes, we can hear you, but I guess you are not able to hear us now.
Screen?
This
Yes,
meeting
bro.
is being recorded.
Yes, bro. We can see your screen also.
Hello?
Yes, we can see your screen.
Here where the Zoom is open.